What if I told you that directly above the sun and directly below it, there are places so strange that almost nobody talks about them? Most people think of the sun as a giant ball of fire floating alone in space. But if you could travel straight upward from the sun, or plunge straight downward through the solar system, what would you actually find? Would it be empty space, hidden worlds, massive structures created by gravity itself, or something even more surprising? Today, we're taking a journey in two impossible directions to uncover what's really above and below our star. And the deeper we go, the stranger the discoveries become. Because the answer isn't what most people expect, and it completely changes how you think about our place in the cosmos. We live out our lives along its surface, swimming in a collective sideways drift that has not wavers for thousands of millions of years. Yet perpendicular to this tabletop lie two vast, pristine wildernesses, the space directly above the North Pole of the Sun and the space directly below its South Pole. For generations, these vertical corridors have remained the ultimate blank spaces on our charts. We have sent probes into the freezing, dark outskirts of Pluto, across the hellish pressures of Venus, and into the crushing radiation belts of Jupiter, but the vertical axis remains almost entirely unbreached. To look straight down upon our solar system from above, to capture a single photograph showing the concentric rings of the planets spinning like a true disk, is an achievement that remains frustratingly out of reach. The obstacle is not a lack of curiosity, nor is it a failure of engineering will. The barrier is an invisible, mathematical prison built out of our own inheritance, the tyranny of inherited velocity. To understand why the vertical sky is so deeply forbidden, we must first confront a silent reality about our home. As you sit quietly listening to these words, you are not at rest. Earth is not merely spinning on its axis. It is hurtling through the void at a speed that defies our terrestrial senses. Every second that ticks by, our planet travels approximately 30 kilometers along its orbital path around the sun. Within a single minute, we are swept nearly 2,000 kilometers through the darkness. Every tree, every mountain, every ocean, and every launch pad on Earth shares this relentless sideways momentum. When a rocket ignites its engines and climbs away from Cape Canaveral or Baikonur, it does not start from zero. It inherits every single meter per second of Earth's 30 kilometer per second orbital velocity simply by having been built on its crust. This inheritance is an extraordinary gift if you wish to travel to destinations that share our flat plane. If a spacecraft wants to journey to Mars or the asteroid belt, it only needs to add a relatively modest push in the direction it is already moving. The rocket uses its fuel to widen its orbit, letting the sun's gravity do the heavy lifting over the vast distances of the disk. But if that same spacecraft wishes to turn 90 degrees and climb straight up out of the flat plane to look down upon the sun from above, that inherited gift turns into a devastating curse. The 30 kilometers per second of sideways motion does not simply vanish. It is a stubborn celestial momentum that forces the spacecraft to loop around the sun in a wide, flat circle, no matter how hard it tries to steer upward. To truly break free of the disk and enter the vertical wilderness, a probe must carry enough rocket fuel to completely erase those 30 kilometers per second of sideways speed, and then generate an entirely new velocity pointing perpendicular to the planetary plane. In the language of spaceflight, this change in velocity is known as delta 5. It is the absolute currency of the cosmos. Every maneuver, every course correction, and every deceleration costs a specific amount of this precious budget. To send a probe to the outermost rim of the solar system, out past the icy worlds of the Kuiper Belt, requires far less delta 5 than sending a spacecraft a fraction of that distance straight up into the empty sky above the sun. The direct vertical climb requires a budget that no chemical rocket built by human hands can supply. We can easily slide along the current of the river, but swimming directly across it to the steep vertical cliffs of the canyon is a feat that breaks our conventional technology. The vertical axis is a realm where the laws of orbital mechanics demand a price we cannot pay with fire and steel alone. The great flattener of the void. The flatness that holds us captive is the ancient fossil imprint of our creation. It is a geometry repeated across every scale of the universe, an inevitable compromise between two fundamental forces, gravity and rotation. Long before the planets were solid spheres, before the sun had even ignited its nuclear fire, our solar system existed as a vast, shapeless cloud of interstellar gas and dust. It was a cold, chaotic mass spanning light years of space, drifting aimlessly through the galactic dark. As the internal gravity of the cloud began to pull its material inward, the entire structure started to contract. But the cloud was not perfectly still. It possessed a faint, collective swirl, a legacy of the turbulent galactic currents that formed it. As gravity drew the gas and dust closer together, that faint swirl began to accelerate, much like a figure skater drawing their arms inward, to spin faster and faster. This is the conservation of angular momentum, a patient law that shapes the cosmos. As the rotation speed quickened, a profound asymmetry emerged. Along the poles of the rotation axis, the directions we consider straight up and straight down, there was no centrifugal force to resist the inward pull of gravity. The material at the top and bottom of the cloud could fall freely toward the center, collapsing downward without impedance. But along the equator of the spin, the outward push of the rotation counteracted the inward tug of gravity. The cloud could not collapse across its axis of rotation without shedding its spin, which physics strictly forbids. Over millions of years, the shapeless cloud performed a beautiful cosmic calculation. The pole-to-pole axis collapsed completely, while the equatorial axis held its ground. What was once a giant, three-dimensional sphere flattened into a wide, thin, rapidly spinning disk. At the dense, hot center of this disk, the sun began to coalesce, swallowing up more than 99% of the cloud's total mass. In the cooling outer rings of the disk, the remaining dust grains began to collide, sticking together to form pebbles, then boulders, then protoplanets, and finally the stable worlds we know today. Every planet accumulated its mass entirely within the boundaries of this original disk, inheriting its flat geometry and its unrelenting sideways motion. Anything that drifted too far above or below the plane was either dragged back down by the collective gravity of the disk, scattered out into the interstellar wastes by close encounters, or simply starved of the material needed to grow. The flatness we see when we look at the paths of the planets is the surviving skeleton of that ancient primordial cloud. It is a pattern echoed in the majestic rings of Saturn, in the blazing accretion disks that encircle black holes, and in the grand sweeping arms of the Milky Way galaxy itself. Flatness is the natural signature of an organized universe. The dust that traces the plane, the ancient disk that birthed the worlds, has long since been swept away, cleared out billions of years ago by the fierce radiation and powerful winds of the young sun. Yet the plane is not entirely empty. A faint, ghostly residue still hugs the planetary tabletop, a delicate reminder of the geometry we inhabit. This is the zodiacal dust cloud, a sparse sheet of microscopic grains that stretches from the immediate vicinity of the sun out past the orbit of Mars. Unlike the primordial disk, this dust is not a remnant of creation, but a product of the modern solar system's quiet, continuous erosion. Deep within the asteroid belt, between the orbits of Mars and Jupiter, ancient space rocks are constantly colliding in absolute silence, grinding each other into finer and finer fragments over millennia. At the same time, icy comets sweeping in from the dark outer edges of the system shed long, trailing veils of dust as they warm under the sun's glare. Because the asteroids and comets that produce this material live and move within the flat planetary plane, the dust they shed remains locked there as well. The subtle pressures of sunlight and the gravitational nudges of the planets keep this microscopic debris confined to a thin, distinct layer. For those who know when and where to look, This dust offers a rare chance to glimpse the true shape of our solar system with the naked eye. On the darkest nights of the year, far from the artificial glare of human civilization, a strange and beautiful phenomenon can be observed shortly after the last light of sunset has vanished from the western sky, or just before the first glow of dawn breaks in the east. A soft, pale pyramid of ghostly light appears, slanting upward from the horizon, tracing a precise path across the constellations of the zodiac. This is the zodiacal light. It is not an atmospheric glow, nor is it related to the auroras that dance near our poles. It is the actual disk of the solar system itself, made visible because billions of tiny grains of rock and ice are scattering the hidden light of the sun back toward our eyes. To look upon the zodiacal light is to see the planetary highway from the inside. From our vantage point within the disk, the dust appears as a dense, luminous band cutting across the dark. But if we could somehow ascend into the vertical sky, looking down from directly above the sun, the zodiacal cloud would reveal its true form, a wide, translucent sheet of cosmic dust, brightest and densest near the central star, and fading into absolute blackness as it extends outward toward the cold berths of the gas giants. The great galactic crossroads. The flat plane of our solar system does not exist in isolation. It is nested inside an incomparably grander architecture, the vast, rotating disk of the Milky Way galaxy. Our galaxy is a majestic wheel of several hundred billion stars, thousands of light-years across, flattened by the very same laws of gravity and rotation that shaped our local neighborhood. However, the universe is rarely arranged in neat, parallel lines. The flat tabletop of our solar system is not aligned with the flat tabletop of the galaxy. Instead, the two planes are tilted with respect to one another at a sharp, dramatic angle of roughly 60 degrees. As the Sun carries its retinue of planets on its long 250 million-year journey around the galactic center, we travel through the darkness leaning over on our side, like a ship tilting into a permanent cosmic wave. This geometric misalignment creates a fascinating contrast when we consider the vertical axes of both systems. From our current position on Earth, deep within the planetary disk, our view of the wider universe is permanently cluttered by our immediate surroundings. When we look along the plane of the ecliptic, our telescopes must peer through the thickest parts of the zodiacal dust cloud and past the glare of the nearby planets. But if we were to travel straight up, arriving at a vantage point directly above the Sun's north pole, the night sky would undergo a breathtaking transformation. The familiar band of the Milky Way, which cuts a predictable path across our terrestrial sky, would appear tilted at a violent, unfamiliar angle. The brilliant, star-dense bulge of the galactic center would shift into an entirely new quarter of the heavens. The constellations that have guided human navigators for millennia would be warped and rearranged by the shift in perspective, offering a view of the cosmos that no human eye has ever witnessed. More importantly, looking straight up or straight down from the sun means looking entirely out of the local dust. The vertical corridors are the cleanest, most transparent portals to the deeper universe available anywhere in our region of space. Below the sun's south pole, the line of sight extends out into a remarkable feature known as the local bubble, a vast, hollow cavern in interstellar space carved out millions of years ago by ancient, dying stars. The southern vertical axis points directly down one of the clearest chimneys of this bubble, offering an unobscured view into the deep intergalactic void beyond. The directions we find hardest to reach are the very directions that offer the clearest view of everything that lies beyond our home. The hidden dynamics of the solar poles. For centuries, our understanding of the sun has been fundamentally incomplete because we have been forced to view it from the side. We look at our star from the equatorial plane, watching sunspots drift across its middle, observing flares erupt from its active belts, and tracing the beautiful looping magnetic arches that rise during eclipses. But studying the sun entirely from its equator is like trying to understand the geography of Earth while being forbidden from ever traveling north of the tropics or south of the equator. You would see the weather of the equator, but you would completely miss the ice caps, the polar vortices, and the deep ocean currents that regulate the global climate. The poles of the sun are not mere borders. They are the control centers of its entire global behavior. It is at the poles that the most profound secrets of solar physics are hidden. Unlike Earth, which is a solid ball of rock, the sun is a churning, fluid sphere of superheated plasma. It does not rotate at a single, uniform speed. The plasma at the solar equator completes a full rotation in about 25 days, while the plasma at the poles takes more than 34 days to make the same trip. This differential rotation acts as a giant, cosmic blender, twisting and stretching the sun's internal magnetic field lines until they become tightly wound, like rubber bands stretched to their absolute limit. Every 11 years, this magnetic tension breaks, resulting in a complete reversal of the sun's global magnetic field. The North Pole becomes the South Pole, and the South Pole becomes the North Pole. This cycle drives the entire rhythm of the solar system, dictating when dangerous solar storms will erupt and when the star will settle into a quiet, fitful slumber. Yet the deep mechanisms that drive this solar dynamo are located precisely within the polar zones, hidden from our view by the extreme foreshortening of our equatorial perspective. When we look at the solar poles from Earth, we see them at a grazing, nearly impossible angle, distorted by the curvature of the sun's surface. We are blind to the deep structural movements occurring there. We cannot accurately measure the slow, churning polar currents that carry magnetic fields from the equator down into the interior of the star, acting as the great conveyor belt of the solar cycle. To truly understand the engine that regulates our star, and by extension, the space environment that surrounds our own planet, we must find a way to climb out of the flatlands and look down into the smoking craters of the solar poles. The wilderness of the fast solar wind. In the early decades of the space age, scientists began to realize that the space between the planets is not an empty vacuum, but a roaring, tempestuous sea filled with a continuous stream of charged particles blowing outward from the sun. This is the solar wind, a relentless torrent of electrons and protons that bathes every world in our system, carving out a giant bubble in the interstellar medium known as the heliosphere. For a long time, the solar wind measured by our satellites near Earth seemed chaotic, turbulent, and unpredictable, fluctuating wildly in speed and density from day to day. But when the first pioneering instruments began to look toward the higher latitudes of the sun, they discovered that the chaos we experience within the planetary disk is merely a local abnormality. The true dominant character of the solar wind can only be found in the vertical sky. Directly above the sun's north and south poles lie immense, stable structures known as coronal holes. These are vast regions where the sun's magnetic field lines do not loop gracefully back down to the surface, forming the closed arches that trap hot plasma near the equator. Instead, at the poles, the magnetic field lines break wide open, stretching straight out into the deep void like long, invisible highways. Because there are no magnetic loops to hold it back, the superheated plasma within the polar coronal holes escapes freely into space, accelerating to astonishing velocities. This is the fast solar wind. While the wind that drifts along the planetary plane crawls outward at a variable 300 to 500 kilometers per second, the fast solar wind from the poles streams out in a steady, unbroken, and beautifully uniform torrent at nearly 800 kilometers per second. The vertical axis of the solar system is, therefore, a place of intense, pristine cleanliness. It is a realm swept clean by a constant, high-speed gale of pure solar plasma, free from the turbulent collisions and magnetic tangles that clutter the equatorial plane. The fast solar wind forms a vast, symmetrical column blowing straight up and straight down out of the star, creating a completely different space environment than the one humanity has inhabited throughout its history. To enter the vertical sky is to step out of the muddy, swirling eddies of the planetary river and into the roaring, crystal-clear rapids of the solar source. The planetary slingshot. Since our chemical rockets lacked the sheer brute force required to erase Earth's sideways orbital speed and climb directly into the vertical sky, humanity has been forced to adopt a more elegant, patient strategy. If we cannot build an engine powerful enough to break out of the disk, we must borrow the necessary energy from the worlds that inhabit it. We must turn to the art of the gravity assist. A gravity assist is one of the most beautiful maneuvers in all of celestial mechanics. It is a method of steering through the solar system without burning a single drop of rocket fuel, relying instead on a precise, mathematical exchange of momentum between a tiny, lightweight spacecraft and an unimaginably massive planet. When a probe flies closely past a world like Venus or Jupiter, it enters that planet's gravitational sphere of influence. From the perspective of the planet, the spacecraft enters its domain, curves around its mass, and leaves with the exact same speed it arrived with. But from the perspective of the stationary sun, a profound transformation has occurred. Because the planet itself is moving rapidly along its own orbit, the spacecraft can hitch a ride on the planet's immense orbital momentum. Depending on the exact angle and distance of the approach, the probe can be slung forward to gain tremendous speed, slowed down to drop into the inner solar system, or redirected sharply onto an entirely new path. The planet, being so colossally heavy, loses an infinitesimally tiny, immeasurable fraction of its orbital speed in the exchange, while the tiny spacecraft receives a monumental change in its velocity. To climb into the vertical sky, mission designers look to Jupiter, the undisputed heavyweight champion of our planetary disk. Jupiter contains more mass than all the other planets, moons, and asteroids in our solar system combined. Its gravitational well is a deep, powerful vortex capable of performing redirects that would be utterly impossible using traditional rocket engines. If a spacecraft is sent along a carefully calculated path that skims over the top or bottom of Jupiter's swirling cloud tops, the giant planet's gravity can seize the vehicle and bend its trajectory by 90 degrees in a single, violent sweep. The sideways orbital velocity that the probe inherited from Earth is wiped away, converted instead into a steep, vertical velocity that hurls the machine straight up, out of the planetary tabletop, and on a long, looping path toward the solar poles. This is the celestial ladder, the only method currently within our technological reach to scale the vertical walls of our cosmic home. The loneliness of the high-latitude traveler. Only a tiny handful of human machines have ever managed to climb high enough out of the flatlands to catch even a fleeting glimpse of this vertical frontier. The most famous and successful of these pioneers was Ulysses, a joint mission between NASA and the European Space Agency, launched in the final decade of the 20th century. Ulysses was a machine designed specifically to do what no other spacecraft had ever attempted, to leave the planetary plane completely and study the sun from above and below. Because no rocket on Earth could provide the necessary energy, Ulysses was hurled across the immense distance to Jupiter. In February of 1992, the probe skimmed past the giant planet's north polar region, using Jupiter's immense mass as a gravitational pivot point. The encounter threw Ulysses into a highly inclined orbit that tilted nearly 80 degrees relative to the planetary plane. For the next 15 years, Ulysses lived a lonely, isolated existence, far outside the comfortable hallway where the rest of humanity's creations reside. It moved along a vast, sweeping ellipse that carried it high above the southern hemisphere of the sun, then diving down through the equatorial plane and climbing back up over the northern polar wastes. The data Ulysses sent back changed our understanding of the heliosphere forever. It was Ulysses that first mapped the grand, uniform structure of the fast solar wind, confirming that the polar coronal holes are permanent fountains of high-speed plasma. It discovered that the sun's magnetic field at the poles is much weaker and more complex than anyone had predicted, and it revealed that the cosmic rays flooding into our solar system from deep space enter far more easily through the clear vertical corridors than through the dusty, crowded planetary disk. Yet, for all its historic success, Ulysses carried a profound limitation. It was a mission focused entirely on fields and particles. It carried no cameras. It could feel the solar wind, measure the magnetic fields, and count the dust grains. But it could not send back a single photograph of what the sun's poles actually look like. It moved through the vertical wilderness in absolute blindness, leaving the visual appearance of the solar poles a tantalizing mystery. The strange dive toward the fire. To bridge this final gap in our vision, modern astronomers have had to devise an even more complex, patient, and counterintuitive dance through the inner solar system. This is the strategy utilized by ESA's Solar Orbiter mission, a sophisticated explorer designed to finally capture the very first close-up, high-resolution images of the sun's polar regions. Unlike Ulysses, which used a single dramatic encounter with Jupiter to leap out of the plane in one giant bounds, Solar Orbiter cannot rely on the giant planet. To take high-quality images, the spacecraft must stay close to the sun, deep within the blistering heat of the inner solar system, far inside the orbit of Jupiter. To climb out of the plane from this close-in vantage point requires a completely different kind of patience. It requires a series of repeated, delicate encounters with the planet Venus. Venus is far smaller than Jupiter, possessing only a fraction of its gravitational muscle. A single flyby of Venus cannot throw a spacecraft out of the planetary disk. But what Venus lacks in raw strength, it makes up for in proximity. Solar Orbiter is locked into a carefully synchronized orbital resonance with the veiled planet. Every few months, the spacecraft loops through the inner solar system and skims past Venus, using the planet's gravity to nudge its orbit just a little bit higher each time. It is a slow, methodical climb, an architectural spiral that gains a few degrees of inclination with every encounter. The spacecraft pays for its vertical ascent not in tons of rocket fuel, but in years of precious mission time. With every pass, the perspective shifts. The flat planetary plane begins to tilt away, and the curved, churning polar regions of our star slowly lift into view. As Solar Orbiter continues its long, patient dance, its inclination will eventually rise high enough to look directly down upon the solar poles, mapping the ancient magnetic conveyor belts and photographing the deep, dark structures of the polar coronal holes with unprecedented clarity. It is a triumph of mathematical ingenuity over the sheer limitations of physics, a mission that demonstrates that if we cannot break the prison of our orbital velocity by force, we can eventually dismantle its walls through the quiet, relentless application of geometry and time. The silence of the vertical sky. When we look back at the long history of human exploration, we see a species that has always been obsessed with horizons. We have crossed oceans, scaled mountains, and mapped the farthest, coldest continents of our world. In the cosmic age, we have continued this outward push, sending our mechanical emissaries along the flat, predictable plane of the disk to uncover the secrets of our sister worlds. But the vertical axis of the solar system reminds us that some of the most profound frontiers are not located across vast distances of space. They are located right above our heads, hidden in a direction we simply do not possess the raw power to easily steer toward. The space directly above and below the sun remains a place of profound, haunting silence, a pristine sanctuary swept clean by the fast solar wind, offering an unobscured view into the deepest architecture of the universe. One day, perhaps, new propulsion technologies, such as immense solar sails that use the continuous pressure of sunlight to gradually cancel out orbital velocity without using fuel, will allow us to traverse these vertical corridors with ease. We will finally take that missing photograph, looking straight down upon the solar system from a vantage point of absolute detachment, seeing the planets as a single, delicate, spinning disk of dust and life. But until that day comes, the vertical sky remains a beautiful testament to the laws that created us. The flatness that holds us captive is the very same flatness that allowed our world to form, the ancient shape of a collapsing cloud that gave us a stable place to stand and look up into the dark. The prison of our velocity is also our cradle. And as we rest here in the quiet currents of the planetary plane, we can take comfort in knowing that the wilderness above and below is waiting, preserved in absolute purity, holding its secrets until we have finally learned how to climb. The dynamics of the polar crowns. As we look deeper into the architecture of the solar poles, we find ourselves confronting a boundary that does not exist anywhere else on the star. This is the region known as the polar crown, a vast circular frontier that rings the high latitudes of both the north and south poles. If the equator is the bustling, chaotic metropolitan center of the sun, packed with volatile magnetic fields and complex sunspot groups, the polar crowns are its ancient, frozen shorelines, marking the transition into the absolute wilderness of the open coronal holes. Along these crowns, the sun's magnetic fields perform a slow, collective migration that takes years to unfold. Throughout the 11-year solar cycle, small fragments of magnetic flux are shredded from decaying sunspots near the equator. These fragments do not simply vanish. They are caught up in a subtle, deep-seated movement of plasma called the meridional flow. This flow acts as a giant, incredibly slow planetary conveyor belt, drifting away from the equator toward the poles at a casual speed of just a few meters per second. As these microscopic bits of magnetism drift northward and southward over the course of years, they accumulate at the boundaries of the polar crowns. Here, they form immense looping walls of cold, dense magnetic plasma known as polar crown filaments. Viewed from the side through our telescopes on Earth, these filaments appear as long, dark, serpentine ribbons suspended high in the solar atmosphere, silhouetted against the blinding brightness of the star below. They are among the largest single structures in the entire solar system, stretching for hundreds of thousands of kilometers across the high latitudes, forming a literal crown around the poles. Because these filaments are held aloft by highly stressed, twisting magnetic field lines, they are inherently unstable. They can sleep quietly for months, tracing the edge of the polar wilderness, like a long mountain range, before suddenly exploding into space in a matter of hours. When a polar crown filament erupts, it launches a colossal bubble of magnetic energy and billions of tons of superheated gas into the void, a phenomenon called a coronal mass ejection. But because these eruptions occur at the top and bottom of the sun, their trajectories are completely different from the storms we are used to tracking near the equator. Instead of sweeping across the orbital paths of Earth and the other planets, these polar eruptions are fired straight up and straight down into the vertical sky. They barrel through the clean corridors of the fast solar wind, expanding into the empty space above and below the solar system like giant, expanding smoke rings. They are massive, energetic events that unfold in absolute isolation, altering the environment of the high latitudes while leaving the flat plane of the planets completely untouched. The mystery of polar heating. To stand directly above the pole of the sun would be to witness a thermodynamic paradox that has baffled physics for more than half a century. This is the mystery of coronal heating, an environmental anomaly that becomes nowhere more stark or pronounced than within the boundaries of the polar coronal holes. Under normal conditions, the laws of thermodynamics are comforting and predictable. As you move away from a source of heat, the temperature drops. If you sit near a campfire, the air grows colder the further you step back into the dark. The core of the sun is a roaring nuclear furnace, reaching temperatures of 15 million degrees. By the time that heat bubbles up to the visible surface, the photosphere, it has cooled down to a relatively modest 6,000 degrees. But as you climb higher still, leaving the surface behind and entering the translucent atmosphere of the corona, the rules of the universe appear to break down completely. Instead of continuing to cool, the temperature suddenly and violently skyrockets, exploding from a few thousand degrees to well over 1 million degrees within a shockingly narrow boundary. Within the polar coronal holes, this heating mechanism takes on an even stranger, more aggressive character. Because the magnetic field lines at the poles are wide open, stretching straight out into the vertical void, the plasma is not trapped in place. It is free to expand and run away into space. Yet, despite this constant cooling from expansion, the ions within the fast solar wind are heated to temperatures that are actually higher than those found in many closed magnetic loops near the equator. Even more remarkably, the heating at the poles is highly selective. Instruments on the Ulysses spacecraft and later space-based observatories revealed that heavier ions, such as oxygen and iron, are heated to temperatures tens of times hotter than the lighter protons and electrons. These heavy atoms are accelerated to extreme speeds, vibrating and racing outward into the vertical sky, as if they are being deliberately targeted by an invisible, cosmic energy source. The leading theory for this polar phenomenon points to a process called ion cyclotron resonance. Imagine the open magnetic field lines at the poles as long, taut guitar strings extending out into the dark. Deep within the churning interior of the Sun, violent convective currents pluck these strings, sending powerful magnetic waves, known as Alfvén waves, rippling upward along the vertical axis. As these waves travel into the thinning plasma of the polar atmosphere, they begin to twist and cascade, breaking down into smaller and smaller vibrations. When the frequency of these magnetic vibrations matches the natural orbital spin of a heavy ion circling the magnetic field line, the ion absorbs the wave's energy instantly, like a swing being pushed at the perfect moment of its arc. This process dumps tremendous amounts of energy directly into the particles, transforming the polar sky into a vast, natural particle accelerator that propels the fast solar wind to its blistering 800 km/s velocity. The shape of the magnetic shield, the vertical axis of our system, is also the place where the fundamental geometry of our cosmic shield is defined. Our solar system is not merely a collection of rocks orbiting a star. It is an active, magnetic kingdom carved out of the local interstellar medium. The boundary of this kingdom is the heliosphere, a giant, teardrop-shaped bubble maintained by the continuous outward pressure of the solar wind. Because the solar wind blows differently depending on where it escapes from the star, the heliosphere itself is highly asymmetric. It is shaped entirely by the contrast between the flat equatorial plane and the vertical polar axes. Throughout the quiet phases of the solar cycle, the slow, turbulent wind from the equator creates a dense, compressed sheet of plasma that extends outward along the planetary tabletop. This is the heliospheric current sheet, a massive, undulating structure that ripples through the inner planets like a spinning ballerina's skirt, carrying the Sun's alternating magnetic polarities to the edges of the disk. But above and below this rippling skirt, the fast solar wind from the poles dominates the sky. It carves out two immense high-pressure reservoirs that push out against the cold gas of interstellar space with incredible force. Because the fast solar wind is so uniform and powerful, the heliosphere stretches significantly further along its vertical axis than it does along its leading equatorial edge. This creates a geometric shield that protects the planets from one of the most dangerous hazards in the deep galaxy, galactic cosmic rays. Cosmic rays are high-energy particles, mostly protons accelerated to nearly the speed of light by distant supernova explosions and active galactic nuclei thousands of light-years away. They rain down upon our solar system from every conceivable direction, threatening to tear through the atmospheres of planets and fry the electronics of human satellites. As these galactic invaders approach our neighborhood, they run headfirst into the outward rushing wall of the solar wind. Within the flat planetary plane, the cosmic rays must navigate through the dense, messy, and turbulent structures of the slow wind and the heliospheric current sheet. This acts as a thick, chaotic buffer, scattering many of the particles and preventing them from reaching the inner solar system. At the poles, however, the situation is completely reversed. The open, straight magnetic field lines of the vertical sky act as a direct, unobstructed entry ramp. Galactic cosmic rays approaching from above the Sun's north pole or below its south pole can slide down the open magnetic highways with relative ease, penetrating much deeper into the inner core of the system before being scattered by the fast wind. The vertical axis is a double-edged sword. It is the path where the solar system breathes out its cleanest, fastest wind, but it is also the wound in our magnetic armor where the deep, unattenuated energy of the wider galaxy can seep back in. The disappearing axis of cosmic balance. The permanence we ascribe to the solar system's geometry is a trick of our short lifetimes. We look at the invariable plane and assume it has always sat precisely where it does tonight, but the vertical axis is actually engaged in a slow, multi-million-year wobble that continuously resets the balance of our cosmic neighborhood. This wobble is driven by the complex, gravitational tug-of-war between the major planets, a phenomenon known as orbital precession. While the Sun contains the overwhelming majority of the system's mass, the planets possess the vast majority of its angular momentum. Jupiter and Saturn, the two gargantuan gas giants, act as the true anchors of the planetary tabletop. Their immense gravitational fields constantly pull and nudge the smaller worlds, including Earth, ensuring that no orbit remains perfectly fixed over geological time. Because Earth's orbit is slightly tilted relative to the true invariable plane of the system, our view of the vertical sky is not stable. Over cycles that last tens of thousands of years, known as Milankovitch cycles, the tilt of Earth's axis of rotation and the orientation of its orbital ellipse slowly shift and rotate in response to the planetary gravitational net. This means that the direction we define as straight up from our perspective is constantly drifting across the background stars. Stars that currently sit directly above our northern horizon, acting as reliable markers of our orientation, will eventually slide away, replaced by entirely different constellations as the planetary disk performs its slow, rhythmic tilt. Even the Sun itself is not perfectly aligned with the invariable plane of its children. The equator of the Sun is tilted by about 7 degrees relative to the average plane of the planetary orbits. This means that as we ride Earth on its annual journey around the star, we are constantly rising and falling through the Sun's true equatorial plane, looking slightly down onto its northern pole in September and slightly up at its southern pole in March. This 7-degree tilt is a tiny, tantalizing window, a brief opportunity for astronomers on Earth to peer just a fraction of a degree further into the high latitude zones during specific months of the year. But it is a teasing view, a reminder of how close we are to the vertical secrets of our star, and yet how completely barred we remain from entering them fully without the assistance of immense planetary slingshots or patient looping orbits around Venus, the cleanest window in the universe to fully appreciate the isolation of the vertical sky. One must contemplate the sheer cleanliness of its void. Within the flat plane of the planets, space is a cluttered, dusty highway. As we look across the disk, our vision is obscured by the zodiacal cloud, the debris fields of ancient comets, the fragments of pulverized asteroids, and the ambient glare of solar light bouncing off billions of tons of interplanetary dust. For astronomers trying to look beyond our solar system to study the earliest, most distant structures in the cosmos, this local dust is a devastating source of noise. It creates a faint, persistent background glow known as the zodiacal foreground emission. This glow behaves like a light-polluted sky over a major city, drowning out the incredibly faint, ancient light of the first galaxies that formed after the Big Bang, the cosmic infrared background. If you want to observe these primordial signals from a telescope located near Earth or Mars, you must spend months performing complex mathematical subtractions, trying to scrub away the local glare of our own solar system's dust, to see the universe hiding behind it. It is a process fraught with uncertainty, a struggle to see through a dirty, grease-stained window. But if we could place an astronomical observatory into a stable orbit directly above the Sun's North Pole, high outside the flatlands of the invariable plane, that window would become instantly pristinely clear. Because the zodiacal dust falls off rapidly with vertical distance, thinning out into absolute nothingness, just a fraction of an astronomical unit above the plane, a polar telescope would look out into a sky that is completely black. From this vertical vantage point, the local light pollution of the solar system would vanish entirely. Astronomers would have an unobscured, crystal-clear view into the deep intergalactic night. They could peer into the furthest depths of time and space, capturing the faint, unattenuated infrared signatures of the very first stars without having to filter out the debris of local asteroid collisions. The direction that is hardest for our rockets to reach is the very direction that offers our science the most flawless view of the infinite universe. It is a place where the local clutter of our origin falls away, leaving nothing but the pure, cold light of the deep cosmos, the cold remnants of the vertical sky. While the major planets and the vast majority of asteroids are strictly confined to the flat tabletop of the invariable plane, the vertical sky is not entirely devoid of permanent residents. At the extreme outer edges of our system, far beyond the orbits of Neptune and the icy worlds of the Kuiper Belt, lies a vast, spherical reservoir of primordial remnants that completely ignores the flatness of the disk. This is the Oort cloud. The Oort cloud is a giant, isotropic shell of icy bodies, containing trillions of comets scattered across light-years of space. Unlike the flat, organized rings of the inner solar system, the Oort cloud is completely spherical, wrapping around the sun from every direction, like a thick, frozen blanket. It is the only structure in our system that fully populates the vertical axis, stretching straight up above the North Pole and straight down below the South Pole. The bodies that live in this icy wilderness are the preserved fossils of the solar system's violent adolescence. Billions of years ago, when the giant planets were still migrating into their current positions, their immense gravitational fields acted as cosmic brooms, sweeping up the icy planetesimals that had formed in the outer disk and flinging them outward in every direction. Many of these icy rocks were thrown entirely into interstellar space, lost to the galaxy forever. But trillions of them were caught on the very edge of the sun's gravitational reach. Over eons, the subtle gravitational nudges of passing stars and the collective tide of the Milky Way galaxy slowly circularized their orbits, transforming what was once a flat distribution of debris into a vast, three-dimensional sphere. Every now and then, the delicate balance of the Oort cloud is disrupted. A passing star, or a nearby cloud of interstellar gas, sends a faint gravitational ripple through the frozen shell, causing an icy body at the top or bottom of the sphere to lose its orbital momentum. The object stalls in its lonely vertical perch, and then begins a long, terrifying fall straight down toward the inner solar system. These are the long-period comets, and when they arrive, they do not follow the planetary highway. They plunge down into our flat world from the vertical sky, arriving from directly above the sun's poles or rising up from the deep void below. They slice through the invariable plane at steep, near-vertical angles, rounding the sun in a brilliant, brief display of ice and fire, before climbing back up into the high-latitude darkness, returning to the spherical isolation of their origin. They are the only natural messengers that regularly travel between our flat hallway and the pristine vertical wilderness that surrounds it. The engineering of the vertical ascent. To appreciate the sheer scale of what missions like Ulysses and Solar Orbiter have accomplished, one must understand the unique, unforgiving engineering constraints that govern any machine designed to leave the planetary plane. Spacecraft built for standard interplanetary missions, such as those traveling to Mars or Jupiter, can rely on a relatively simple, predictable architecture. They remain within the flat plane, which means their solar panels can be permanently oriented toward the sun, and their main antennas can easily point back toward the tracking stations on Earth. But the moment a spacecraft enters a high-inclination orbit and begins to climb into the vertical sky, those simple geometric alignments are completely shattered. As the probe rises above the sun's equator, the relative positions of the Earth, the sun, and the spacecraft are constantly shifting through 3 dimensions in a way that terrestrial engineers rarely have to manage. Consider the challenge of communications. A polar spacecraft must maintain a constant, high-speed data link with Earth using a highly directional dish-shaped antenna. Within the planetary plane, the antenna only needs to rotate left or right along a single axis to follow Earth's movement. But from a high, vertical vantage point, the Earth appears to spin in a rapid, complex circle far below the spacecraft's floor, requiring the antenna to continuously track in multiple axes at once, searching for a tiny blue speck lost against the immense background of the planetary disk. Thermal management becomes an even more severe nightmare. Solar Orbiter, because it must fly close to the Sun to photograph its poles, must endure an environment of absolute extremes. The front of the spacecraft faces a blistering inferno of solar radiation, with temperatures reaching well over 500 degrees Celsius, hot enough to melt lead. To protect its sensitive cameras, the vehicle must be shielded by an immense, multi-layered heat shield made of high-tech titanium sheets coated in a specialized black calcium phosphate powder. Yet because the spacecraft is climbing high out of the plane, its sides and back are constantly exposed to the absolute freezing cold of deep space, dropping to nearly -200 degrees. The machine must exist in a state of permanent thermal schizophrenia, with its nose burning in a solar furnace, while its tail freezes in the interstellar dark. Every line of code, every mechanical joint, and every electronic component must be designed to withstand these violent structural stresses, ensuring that the cameras can peek through tiny, motorized doors in the heat shield to capture the polar secrets without melting the delicate instruments hiding behind them. The long, unhurried sleep of discovery. The exploration of the vertical sky is an exercise in ultimate patience. In our modern world, we have grown accustomed to near instantaneous results. We launch a satellite into low Earth orbit, and it begins transmitting images within hours. We send a lander to Mars, and we are viewing its footsteps on the red soil within a matter of days. But the vertical axis rewards no one who is in a hurry. Because we must use the intricate looping gravity assists of Venus or the immense distances of Jupiter to climb out of the plane, a mission to the solar poles is measured not in months but in decades. It is a journey that unfolds across generations of scientists, requiring an unhurried long-term commitment that is rare in human history. When a spacecraft commits to its vertical trajectory, it enters a long, silent phase of orbit shaping. It loops through the inner solar system, swinging past Venus year after year, gaining just a few degrees of tilt with every encounter. To the casual observer, the machine appears to be going nowhere, trapped in a repetitive, endless circle around the Sun. Yet, during this long sleep, the geometry is quietly and relentlessly doing its work. The inclination is climbing. The planetary plane is leaning over. The familiar world we built our science upon is slowly flattening out into an edge-on line, and the great, unmapped poles of our star are gradually turning to face the instruments. It is a beautiful, slow-motion ballet that reminds us of the true scale of the place we inhabit. The flatness of our solar system was not built in a day. It took millions of years of gravitational collapse, rotation, and settling for the primordial cloud to flatten into the disk we ride tonight. It is only fitting that the process of escaping that disk, of climbing out of the long sideways current we were born into, should require a similar, patient investment of time. As we rest here within the comfortable, thin plane of our home, we can look up toward the zenith of our sky and down toward the nadir beneath our feet, knowing that those vertical corridors are not empty voids, but pristine reservoirs of solar energy, galactic clarity, and ancient primordial history. They are the ultimate frontiers of our local neighborhood, a realm where the wind blows steady and fast, where the dust of our creation vanishes, and where the true, three-dimensional architecture of our cosmic home finally reveals itself to anyone who possesses the patience to make the climb. The solar dynamo and the polar depths. To look at the poles of the Sun is to look into the womb of its magnetic life. Near the equator, we observe the chaotic, dramatic outputs of this life, the colossal sunspot groups that can span many times the diameter of the Earth, the violent flares that snap across magnetic loop systems, and the twisting arcades of plasma that can destabilize and fracture in a matter of minutes. But these are merely the expressions of a deeper machine, a global generator hidden deep within the interior of the star, known as the solar dynamo. The solar dynamo relies on an intricate, continuous cycle of magnetic conversion that loops between the equator and the poles, transforming the very nature of the sun's internal fields over its 11-year cycle. This machine operates on two main axes of motion. The first is the differential rotation we have already observed, the fact that the sun's equator spins significantly faster than its polar latitudes. This rapid equatorial motion catches the sun's internal north-south magnetic field lines and drags them horizontally around the star, wrapping them tightly around its interior like thread around a spool. This process is called the omega effect, and it amplifies the magnetic field to immense strengths, creating the dense, horizontal tubes of magnetism that eventually bubble up to the surface to form sunspots. But if this were the only mechanism at play, the sun's magnetic fields would eventually choke themselves, becoming hopelessly wound up and tangled until the entire generator ground to a halt. To reset the system, the sun relies on a second, far more patient movement, the alpha effect. As the twisted tubes of magnetism rise through the turbulent, boiling convection zone toward the surface, the Coriolis force, generated by the sun's rotation, twists them into new orientations. These twisting structures dissolve, and their remnants are caught up by the slow northward and southward meridional currents, which carry them like a gentle tide away from the equator and dump them into the polar reservoirs. This accumulation at the high latitudes is the vital, missing half of the solar cycle. When the magnetic fields reach the poles, they annihilate the existing opposite magnetic polarity that has resided there for the previous 11 years. Over the course of several years, the old polar fields are completely erased, replaced by a fresh, opposite magnetic orientation. Once the poles are fully charged with this new polarity, the deep conveyor belt sinks back down into the solar interior, carrying the newly minted polar fields back toward the equator, where the differential rotation can begin wrapping them up all over again. Without the poles, the solar dynamo cannot breathe. It is the deep polar sink that allows the sun to shed its old magnetic skin and birth the next cycle of activity. Yet, because we have been stranded within the flat planetary plane, our measurements of this polar field are highly uncertain. We are forced to view the high-latitude fields through a thick, obscuring perspective, estimating their strength based on grazing, foreshortened observations. If our calculations of the polar magnetic strengths are off by even a small fraction, our ability to predict the intensity of future solar cycles collapses. To truly master the forecasting of space weather, to protect our global electrical grids and our orbital communications from the next great solar superstorm, we must have a permanent, clear view looking straight down into the polar magnetic basins, watching the global currents deposit their magnetic cargo in real time. The interplanetary magnetic carpet. As the open magnetic field lines stretch upward and downward out of the polar coronal holes, they carry a hidden structural architecture that maps out across the entire volume of the vertical sky. This is not a smooth, featureless highway of magnetic force, but a complex, vibrating fabric often referred to as the interplanetary magnetic carpet. Even though the polar regions look remarkably calm and dark in ultraviolet images compared to the active equator, they are actually teeming with small-scale, continuous activity. The surface of the polar photosphere is covered in a dense network of supergranular cells, giant boiling bubbles of plasma that can be 30,000 kilometers wide. As these cells churn and push against each other, they concentrate small pockets of intense magnetic field along their boundaries, creating a patchwork of tiny, tightly compressed magnetic loops that cover the entire polar crust. Every day, thousands of these tiny loops collide, break, and reconnect with the giant, open magnetic field lines that extend out into the vertical void. This continuous process of magnetic reconnection releases sudden, sharp bursts of thermal energy. launching microflares and miniature jets of plasma straight up into the polar sky. These jets, known as spicules and macrospicules, shoot upward at speeds exceeding 100 kilometers per second, rising thousands of kilometers above the solar surface like a vast forest of burning needles before dissolving into the lower corona. This endless, crackling activity acts as a collective loudspeaker, sending continuous acoustic and magnetic vibrations rippling upward along the open polar highways. These vibrations do not fade away. They travel deep into the vertical sky, shaking the fast solar wind and creating a highly textured, turbulent magnetic environment far above the star. When a spacecraft like Ulysses or Solar Orbiter climbs out of the planetary plane and into this high-latitude domain, it steps onto this vibrating carpet. Its magnetometers record a continuous, rhythmic pulsing of magnetic waves that have traveled straight out from the solar core without ever being distorted by the complex, looping structures of the equator. The vertical sky is a pure, unedited recording of the sun's internal heartbeat, a place where the magnetic signature of the star can be read without the noise and static of the planetary disk. The great vertical shadow of the corona. If you were to stand in the deep, void millions of miles directly above the sun's north pole during a period of minimum solar activity, the visual spectacle would be completely alien compared to anything we observe from Earth. From our equatorial vantage point, a total solar eclipse reveals a highly structured, asymmetric corona. We see bright, long, blade-like shapes called helmet streamers, stretching millions of kilometers out into space along the equator, while the poles look relatively naked, decorated only by short, delicate fans of light called polar plumes. But from above, the asymmetry vanishes, replaced by a majestic, sweeping circularity. The bright helmet streamers, which appear as individual spikes from the side, would be revealed as a continuous, ring-shaped wall of light girdling the equator of the star far below your feet. The poles themselves would appear as a dark, cavernous shadow at the center of this ring, a vast, hollow chimney through which the fast solar wind pours out into the universe. This dark polar void is a direct consequence of the temperature and density variations that define the high-latitude atmosphere. Because the magnetic fields are open, the plasma is not trapped and compressed. It is free to expand rapidly, dropping its density to a fraction of the values found near the equator. In the world of solar physics, lower density means less light emission, transforming the polar corridors into immense, cool, dark shadows that contrast sharply with the brilliant, glowing belts of the equatorial streamer zone. This vertical shadow stretches across the entire inner solar system. As the fast solar wind rushes out of the dark polar chimney, it creates a vast region of low-density space that extends outward for billions of miles above and below the star. It is an architectural feature of our solar system that is completely invisible to anyone who remains confined to the planetary tabletop. We live out our history in the dense, bright, messy exhaust of the equatorial streamer belt, completely oblivious to the fact that just 90 degrees above us, the solar system opens into a clean, dark, high-speed cathedral of absolute symmetry. The acoustic architecture of the solar interior. The vertical axis of the solar system also holds the key to a science that allows us to look directly through the opaque, blinding mass of the sun and map its deepest internal structures. This is helioseismology, the study of the acoustic waves that continuously ripple through the interior of our star. The sun is an incredibly noisy place. The violent, turbulent boiling of plasma in its outer convection zone creates a relentless cacophony of sound waves that travel deep into the solar interior, bouncing off the dense inner layers and refracting back toward the surface. These sound waves cause the entire surface of the sun to gently rise and fall, oscillating in a complex pattern of millions of individual acoustic modes. By using highly sensitive instruments to measure the rise and fall of this surface plasma, a technique based on the Doppler shift of solar light, astronomers can reconstruct the path that these sound waves took through the interior of the star. It is exactly analogous to how geologists use earthquake waves to map the hidden crust, mantle, and core of the Earth. Helioseismology has allowed us to discover the depth of the solar convection zone, to measure the rotation speed of the Sun's deep core, and to track the movement of giant subsurface rivers of plasma long before they form sunspots on the surface. But helioseismology suffers from a fundamental geometric blind spot when practiced entirely from the planetary plane. Because sound waves travel through 3 dimensions, many of the most important acoustic modes loop straight through the deep polar regions, traveling from the high northern latitudes down through the core and rising again at the high southern latitudes. When we observe the Sun from its equator, these polar crossing sound waves are viewed at an extreme, grazing angle near the limb of the solar disk. The signal becomes distorted, compressed, and lost in the noise of the horizontal surface movements. We are essentially deaf to the acoustic notes that resonate along the vertical axis of the star. By climbing high out of the plane and looking straight down onto the poles, a spacecraft can look directly at the center of these polar acoustic networks. It can measure the vertical rise and fall of the polar plasma with absolute precision, completing our acoustic map of the star. This vertical perspective allows us to hear the full orchestra of the solar interior, unlocking the true rotation speed of the polar core and revealing the deep, hidden origin of the global currents that regulate the solar cycle. The preservation of primordial dust. As we move away from the blinding fire of the central star and look further out along the vertical corridors, we find that the cleanliness of the vertical sky is not just an aesthetic marvel. It is a time capsule that preserves the ancient history of our chemical origin. Within the flat plane of the planetary disk, the dust grains of the zodiacal cloud are constantly being altered, processed, and destroyed. They are subjected to intense, ongoing gravitational disruptions from the planets, which stir up their orbits and cause them to collide at high speeds, shattering into ever smaller fragments. They are baked by the dense radiation of the equatorial plane and eroded by the turbulent streams of the slow solar wind. Over billions of years, this continuous mechanical and thermal processing has altered the original structure of the planetary debris, erasing the chemical signatures of the primitive material from which our world was constructed. But the dust grains that manage to escape into the high latitudes, or those rare primitive grains that drift into our system from interstellar space along the vertical axis, experience a completely different, far more gentle environment. Because the vertical sky is free from the gravitational perturbations of major planets, dust grains can orbit the Sun at high inclinations and absolute stability, moving along long, unhurried paths that never intersect with the destructive machinery of the asteroid belt or the gas giants. Furthermore, the fast solar wind that blows through the polar corridors is remarkably uniform and clean. It exerts a steady, predictable radiation pressure on the high-latitude dust, slowly drawing the grains inward toward the star in a smooth, spiral trajectory known as the Poynting-Robertson effect. This movement is so gentle that the internal crystal structures and chemical compositions of the grains are perfectly preserved. If a human spacecraft traveling through the vertical sky carries a sophisticated dust analyzer, an instrument capable of capturing microscopic grains and vaporizing them with a laser to read their chemical fingerprint, it can sample an undegraded record of the primitive solar nebula. It can analyze dust that has remained frozen in its original state since the birth of the planets, offering a pristine look at the raw elements, organic compounds, and water-bearing minerals that filled our original cloud 4.5 billion years ago. The directions we find hardest to reach are the very directions where the universe has carefully stored the unblemished blueprints of our identity. The cosmic ray fountain. The open vertical corridors above and below the Sun do not merely allow galactic cosmic rays to seep into our solar system. They also act as a majestic, high-speed exit ramp for the most energetic particles produced by our own star. During periods of high solar activity, when the polar crowns fracture and giant filaments erupt into the vertical void, the Sun launches massive bursts of solar energetic particles, Protons and electrons accelerated to relativistic speeds by the snapping of magnetic field lines. Within the planetary plane, these energetic particles are caught up in the tightly wound, spiral magnetic fields of the slow solar wind, a configuration known as the Parker spiral. Because the equator is spinning so fast, the magnetic field lines are dragged into a shape resembling a giant, horizontal lawn sprinkler pattern. Particles traveling along these spiral lines must take a long, winding, tortuous path to escape into deep space, constantly colliding with magnetic irregularities and bouncing backward and forward within the disk. But at the poles, where the rotation has no linear velocity and the field lines stretch straight out into the cosmic dark, there is no spiral twisting. The vertical field lines are almost perfectly straight, extending outward like the spokes of a giant bicycle wheel. When solar energetic particles are launched into the polar coronal holes, they find themselves on a cosmic superhighway. They accelerate outward along the vertical axis without impedance, reaching the outer edges of the heliosphere in a matter of hours. The poles act as a giant, continuous fountain, spraying high-energy particles straight up and straight down out of the solar system at speeds that approach the velocity of light. This vertical particle fountain creates a unique radiation environment far above the star. It is an environment of extreme clarity and directionality, where the particles move in a single, unified stream away from the source. For engineers designing future interstellar probes, machines that will one day have to leave our solar system entirely to journey to other stars, the vertical axis provides a highly predictable, high-speed current that can be used to ride out of the heliosphere, using the straight magnetic highways of the poles to slide cleanly into the interstellar void without having to fight through the turbulent, unpredictable magnetic walls of the planetary tabletop. The geometry of the interstellar drift. To understand the full complexity of the space that waits above and below the Sun, we must look beyond the boundaries of our own system and consider how our entire heliospheric bubble moves through the wider galaxy. The Sun is not stationary within the Milky Way. It is hurtling through the local interstellar cloud at a speed of roughly 26 kilometers per second, steering toward a point in the sky near the boundary of the constellations Hercules and Lyra. This galactic motion creates a powerful, continuous headwind of interstellar gas, mostly neutral hydrogen and helium atoms, that blows through our solar system like a relentless wind tunnel. Because this interstellar wind arrives from a specific direction within the galactic plane, it hits our heliospheric shield at a sharp angle, creating a distinct upstream bow where the bubble is compressed, and a long, trailing downstream tail that stretches for billions of miles behind the Sun like the wake of a ship. This interstellar drift interacts with the vertical axis of our solar system in a fascinating geometric compromise. Because the plane of the planets is tilted by 60 degrees relative to the galaxy, the interstellar wind does not blow horizontally across our planetary tabletop. Instead, it blows across the disk at a steep, slanting angle, plunging down through the northern vertical sky and exiting through the southern high latitudes. This means that the space directly above the Sun's north pole is the great windward porch of our solar system. It is the place where the pristine, unaltered material of the galaxy first collides with the outer boundary of our star's influence. Neutral interstellar atoms can slip past the magnetic shield of the heliosphere and stream deep into the northern vertical corridor, traveling all the way into the inner solar system before being ionized by the Sun's ultraviolet light. The space below the South Pole, by contrast, is the protected, downstream leeward sanctuary. It is a region sheltered by the entire mass of the solar wind, a long, quiet wake where the interstellar gas has been thinned, filtered, and repelled by the outbound momentum of the fast solar wind. The vertical axis is thus divided into two completely different cosmic regimes: a northern sky that acts as a direct, open portal to the modern chemical reality of the local galaxy, and a southern sky that remains an isolated, pure refuge governed entirely by the outbound energy of our own star. The limits of human vision. The human brain is an evolutionary product of a flat world. We evolved to navigate across two-dimensional landscapes, savannas, plains, and coastlines, where the vertical dimension was limited to the height of a tree or the steepness of a local cliff. When we entered the space age, we carried this flat bias with us, projecting our terrestrial maps out into the cosmos, treating the plane of the planets as the natural, default orientation of the universe. This bias is reflected in the very design of our space-based observatories. Nearly every great space telescope we have ever launched, from Hubble to the James Webb Space Telescope, is positioned within the flat plane of the Earth's orbit, floating at stable gravitational points that keep them locked within the dusty, crowded corridor of the ecliptic. From these positions, they can look at distant galaxies and nebulae, but they can never escape the local light pollution of the zodiacal cloud. The missing photograph, the view looking down upon our solar system from above, is a symbol of our geometric confinement. We have mapped the canyons of Mars, measured the wind speeds of Neptune, and stood on the icy nitrogen plains of Pluto, but we remain visually blind to the true holistic shape of our home. We cannot see the concentric tracks of the world spinning together in their flat sheet of creation. We can only infer their geometry from our position inside the hallway. To capture that single, transformative image requires a fundamental shift in our engineering imagination. It requires us to build missions that are not designed to visit a specific destination, but to visit a perspective. It requires us to spend years of mission lifetime, to burn through complex sequences of planetary gravity assists, and to build heat shields capable of enduring absolute fire, simply to reach a point in empty space where there is nothing to touch, nothing to land on, and nothing to harvest. Nothing but a view. Yet, history reminds us that perspective is the most powerful catalyst for human understanding. When the crew of Apollo 8 rounded the moon in December of 1968 and captured the famous Earthrise photograph showing our small, blue, fragile planet rising above the barren, cratered lunar horizon, it did not add a single new fact to our textbooks. We already knew Earth was blue. We already knew it was round. But seeing that reality from an external perspective transformed our collective consciousness forever, birthing the modern environmental movement and forcing us to confront the absolute isolation of our existence. A photograph of the solar system from above would offer a similar, profound calibration. It would shatter our illusion of cosmic centrality, showing our entire world as a microscopic speck of dust floating within a thin, fragile sheet of light, surrounded on all sides by the deep, dark, and monumental vertical wilderness of the universe. It would be a visual confirmation of our true place in the architecture of the void, a reminder that we are merely a local, sideways anomaly, living out our history on a temporary table of dust, the solar sail and the vertical future. As we look toward the future of space exploration, it becomes clear that if we are ever to truly conquer the vertical sky and establish a permanent presence within its clean corridors, we must abandon our reliance on chemical rockets. We must transition from machines that burn fuel to machines that harvest the natural forces of the environment itself. The key to this vertical future is the solar sail. A solar sail is an elegant, lightweight structure that carries no engines and no fuel tanks. Instead, it consists of an immensely large, paper-thin sheet of highly reflective material, such as aluminized mylar or advanced carbon fiber, supported by a lightweight framework of composite booms. It works by exploiting a fundamental property of light, radiation pressure. Although photons have no rest mass, they carry momentum. When light from the sun strikes the reflective surface of a solar sail, the photons bounce off the mirror-like material, transferring their momentum to the sail and delivering a tiny microscopic push. Near Earth, this force is incredibly small, equivalent to the weight of a single postage stamp resting on your hand. But unlike a chemical rocket, which fires its engines for a few intense minutes before running out of fuel and coasting for the rest of its journey, a solar sail receives its tiny push continuously, 24 hours a day, 365 days a year, for as long as the sun continues to shine. This constant, unceasing acceleration accumulates over time into monumental changes in velocity, delivering delta, 5 budgets that no chemical or nuclear engine could ever hope to match. For the challenge of the vertical axis, a solar sail is the ultimate mathematical weapon. To climb out of the planetary plane, a solar sailing spacecraft can tilt its giant mirror at an angle relative to the incoming sunlight. By reflecting the light slightly backward along its path of travel, the sail can continuously slow down the spacecraft's inherited sideways orbital velocity. As the 30 km per second sideways speed is gradually erased by the relentless pressure of light, the sun's immense gravity begins to draw the spacecraft inward. At the same time, the sail can direct a portion of the reflected light sideways, generating a continuous, vertical lift that pushes the machine straight up out of the planetary tabletop. Within a few years of continuous sailing, the spacecraft can achieve a completely stationary, non-orbiting vantage point directly above the Sun's North Pole, a feat known as a statite orbit. Once positioned in this stable vertical perch, a solar sailing observatory would never drop back down into the disk. It would float permanently above the star, balancing the inward tug of solar gravity with the outward pressure of solar light, acting as a permanent, unchanging sentinel over the high latitudes. From this position, human instruments could map the polar magnetic cycles continuously, track the eruptions of the polar crown filaments without interruption, and look out through the cleanest window in the universe to study the deep cosmos with absolute clarity. The solar sail transforms the very light that blinds us into the ladder we use to climb above it, the rhythm of the vertical landscape. As we bring this long, quiet consideration of the vertical axis to a close, we are left with a picture of a solar system that is far more dynamic, spacious, and three-dimensional than our everyday language implies. We live on a flat world, orbiting a flat star, locked inside a flat plane of historical rotation. But that flatness is merely a local consensus, a compromise reached by a cloud of dust 4.5 billion years ago. Perpendicular to that consensus lie the vertical corridors, two immense symmetrical wildernesses that have remained almost completely untouched by human history. They are realms defined by absolute purity, where the fast solar wind blows in an unbroken, high-speed gale, where the magnetic carpet vibrates with the unedited heartbeat of the solar interior, and where the ancient, undegraded dust of our creation drifts in silent, eternal circles. To enter this landscape is to step out of the planetary current, to break the prison of our inherited velocity, and to see our home for what it truly is, a temporary, beautiful disk of matter spinning within an infinite, three-dimensional void. The directions we call up and down are not empty spaces. They are the portals through which our star breathes, the windows through which the galaxy enters, and the pathways along which our future understanding must eventually climb. The night is deep now, and the long, unhurried mechanics of the sky continue their patient work without our assistance. The sun is turning on its tilted axis. The polar currents are carrying their magnetic cargo to the high crowns. The fast wind is roaring out into the vertical dark, and the long-period comets are beginning their silent. Thousands of years fall from the spherical heights of the Oort cloud, the heliopause on the vertical border. When we extend our gaze along the vertical axis past the inner core of the solar system, past the distant orbits of the gas giants, and even past the spherical fringes of the inner Oort cloud, we eventually arrive at the absolute frontier of our star's sovereignty, the heliopause. Within the flat planetary plane, this boundary is a site of violent compressed friction. As the equatorial solar wind rams into the incoming interstellar medium, it creates a turbulent, crowded shock zone that has been probed by the aging Voyager spacecraft. But along the vertical corridors, the heliopause takes on an entirely different structural character. Because the fast solar wind from the poles travels with nearly twice the velocity and significantly more uniform momentum than the equatorial wind, it pushes the boundary of interstellar space much further away from the Sun. The vertical heliopause is not a blunted, compressed wall. It is a long, elegant dome, stretching upward and downward into the galactic void like the polished tips of a cosmic capsule. This means that the physical size of our solar system is dramatically larger along its vertical axis than it is along its horizontal tabletop. A spacecraft attempting to leave the solar system through the traditional planetary plane will encounter the termination shock and the heliopause relatively early, running into a dense wall of scrambled, stagnant magnetic fields. But a probe sent straight up through the northern polar chimney would have to travel billions of kilometers further into the dark before it finally pierced the outer boundary of the sun's influence. When it finally arrived at that distant vertical border, the transition into the galaxy would be uniquely pristine. Within the disk, the boundary is messy, cluttered with trapped galactic dust, compressed magnetic fields, and turbulent eddies created by the sideways motion of the heliosphere dragging through the interstellar cloud. At the poles, the spacecraft would experience a clean, laminar transition. It would slip out of the outbound, fast solar wind and directly into the unattenuated, slanting stream of the interstellar medium without the noise of a cosmic traffic jam. It would be the ultimate exit, a doorway into the wider Milky Way that opens onto an empty, unobstructed cosmic highway. The dynamics of interstellar filtration. The vertical dome of the heliopause acts as an extraordinary natural sorting machine for the matter that attempts to enter our solar system from the wider galaxy. This process, known as interstellar filtration, operates with maximum efficiency along the vertical corridors above and below the Sun. The local interstellar cloud through which our system is currently drifting is a mixture of two components: ionized plasma and neutral gas. The ionized component consists of free electrons and charged atoms that are deeply entangled with the galactic magnetic field. When this interstellar plasma slams into the outer boundary of the heliosphere, it cannot cross the magnetic lines of force generated by the solar wind. Instead, it is deflected around the outside of the bubble, flowing along the flanks of the vertical dome like water parting around the bow of a submarine. The solar system, even along its open poles, remains completely closed to the charged, electrical matter of the deep galaxy, but the neutral interstellar gas, predominantly neutral hydrogen, helium, and oxygen atoms, is entirely indifferent to magnetic fields. These neutral particles do not feel the repelling push of the solar wind's magnetic armor. As the interstellar headwind strikes the northern vertical dome, these neutral atoms pass straight through the boundary without dropping a single meter per second of their speed. They drift into the northern vertical corridor as uninvited galactic ghosts, descending silently toward the inner solar system at 26 kilometers per second. As these neutral atoms fall closer to the Sun, they encounter an increasingly intense barrage of solar ultraviolet radiation and the outward rush of the fast solar wind. This creates a zone of absolute destruction for the incoming gas. Through a process called charge exchange, an outbound proton from the fast solar wind can steal an electron from an incoming neutral interstellar hydrogen atom. In an instant, the galactic intruder is transformed into a charged ion, caught up by the solar magnetic field and flung backward out of the system along the vertical axis. The helium atoms, however, are far tougher. They possess a high ionization potential, allowing them to survive the solar radiation barrage and penetrate deep into the inner sanctum of the system, passing directly over the Sun's north pole at close range. By measuring the density, speed, and temperature of these surviving helium atoms along the vertical axis, space-based instruments can sample the raw, unaltered physical conditions of the galactic cloud outside our shield. The northern vertical corridor is a natural laboratory where the modern galaxy delivers its raw ingredients directly to our doorstep, offering a sample of interstellar space that can be collected without ever leaving the gravitational comfort of our central star. The acoustic waves of the chronosphere. To understand the full vertical architecture of the solar atmosphere, we must examine a thin, vibrant layer sandwiched between the visible surface and the ultra-hot corona. This is the chromosphere, a jagged, burning red layer of plasma that acts as the primary energetic transition zone of the star. Along the vertical axis, the chromosphere behaves like the skin of a giant drum, continuously vibrating with acoustic energy that escapes from the interior. Within the equatorial regions, the chromosphere is an chaotic, fractured landscape dominated by strong, horizontal magnetic fields. These fields trap the plasma, creating complex networks of bright plages and dark filaments that suppress the upward movement of acoustic waves. The sound energy is largely bottlenecked, forced to travel sideways or heat the local magnetic loops until they erupt. But at the poles, inside the open geometry of the coronal holes, the vertical magnetic field lines act as an array of acoustic pipes. The acoustic vibrations generated by the violent, boiling granules at the surface can transition freely into the chromosphere, traveling straight up along the magnetic channels. As these sound waves climb into the thinner, less dense layers of the upper chromosphere, their amplitudes grow exponentially, transforming from gentle acoustic oscillations into violent, supersonic shock waves. These vertical shock waves dump tremendous amounts of mechanical energy into the polar chromosphere, causing it to glow fiercely in the hydrogen alpha line of the spectrum. It is a region characterized by a continuous, microscopic boiling, where millions of small-scale acoustic shocks are bursting every second like popcorn. This acoustic dumping provides the foundational energy that lifts the polar plasma into the lower corona, preparing it to be accelerated by the ion cyclotron resonance into the fast solar wind. If we could observe the polar chromosphere from directly above, we would see a beautiful, uniform mesh of acoustic cell structures, a global pattern of sound nodes and antinodes vibrating in perfect harmony with the internal resonances of the star. It is a view that is completely flattened and obscured from our equatorial perspective, leaving the fundamental acoustic inputs of the solar atmosphere hidden in plain sight along the unseen axis. The geometry of the galactic alignment. When we contemplate the 60-degree tilt between the planetary tabletop and the flat plane of the Milky Way galaxy, we uncover a deeply profound geometric relationship that dictates how our solar system interacts with the wider cosmos over immense stretches of time. This alignment is not static. It is a dynamic historical crossroads. Our solar system does not orbit the galactic center in a neat, level circle. As it circles the distant galactic core every 250 million years, it also performs a slow, vertical bobbing motion, weaving up and down through the dense mid-plane of the galactic disk like a horse on a carousel. Currently, our system sits roughly 30 light-years above the galactic equator, moving upward into the northern galactic hemisphere. This vertical bobbing means that the environment along our solar system's poles is constantly changing over millions of years. When the Sun sits deep within the dense midplane of the galaxy, the vertical axis is subjected to intense gravitational tides from the surrounding stars and gas clouds. These tides compress the spherical shell of the Oort cloud, sending massive showers of comets plunging down from the vertical sky into the inner planets, potentially triggering global extinction events on Earth. Currently, as we climb higher out of the galactic plane, the vertical corridors are opening into an increasingly empty, pristine environment. The gravitational tides are relaxing, and the inflow of interstellar dust along the vertical axis is settling into a quiet, predictable rhythm. By studying the ancient cratering records on the moons of the outer planets, specifically looking at craters located on their high northern and southern polar crusts, astronomers can read the historical record of this galactic bobbing. Craters located along the planetary equators record the chaotic, localized collisions of asteroids within the disk. But craters located at the extreme planetary poles record the historic impacts of comets that dropped out of the vertical sky, offering a pristine, geological diary of our system's journeys through the changing environments of the Milky Way. The vertical axis is a bridge that connects the local history of our planets with the grand, deep-time choreography of the galaxy itself. The polarization of the vertical sky. For an astronomer operating a telescope from a vertical vantage point above the Sun's North Pole, the very light of the stars would reveal a property that is hidden from our terrestrial observatories. This is the phenomenon of interstellar polarization, a subtle alignment of light waves that maps out the magnetic anatomy of our galactic neighborhood. As starlight travels through the deep space between the stars, it must pass through microscopic grains of interstellar dust. These grains are not spherical. They are elongated, needle-like fragments of carbon and silicates. In the presence of the weak, sweeping magnetic fields that thread through the Milky Way, these spinning dust grains align themselves perpendicular to the magnetic lines of force, acting as a giant cosmic polarizing filter. When unpolarized starlight passes through this array of aligned dust, the light waves vibrating along the length of the needles are absorbed, while the light waves vibrating perpendicular to them pass through unimpeded. By the time that starlight reaches a telescope, it carries a distinct linear polarization that reveals the exact orientation of the galactic magnetic field lines along the line of sight. From our position within the flat planetary plane, trying to measure this interstellar polarization is a nightmare of local interference. The light from distant stars must first pass through the thick, swirling mess of our own zodiacal dust cloud. This local dust scatters the light, adding its own intense, variable polarization that smears out the delicate galactic signal. It is like trying to read a faint, beautifully written letter through a window covered in condensation and rain. But from the clean vantage point of the vertical sky, high above the zodiacal tabletop, the local interference drops to zero. A polar telescope would look out through a completely uncluttered window, capturing the pure, unaltered polarization of starlight from thousands of light years away. This would allow astronomers to construct a flawless, three-dimensional map of the galaxy's magnetic field lines, tracing the invisible forces that guide the formation of new stars, regulate the flow of cosmic rays, and shape the majestic spiral arms of our cosmic city. The vertical axis is a sanctuary of structural clarity, a place where the local debris of our solar system falls away, leaving the magnetic skeleton of the universe bare and readable. The isolation of high-latitude planetary systems. The flatness that dominates our solar system is not a unique anomaly. It is a universal law of planet formation that we see repeated across the galaxy. Thanks to modern space telescopes, we have discovered thousands of exoplanets orbiting distant stars, and nearly all of them reside within flat, organized disks that match the geometry of our own invariable plane. This realization forces us to confront a profound truth about the nature of cosmic isolation. If a technological civilization were to arise on a planet orbiting a star with a highly inclined or vertical planetary system relative to the galactic plane, their experience of the night sky and their journey into spaceflight would be radically different from our own. Imagine a world born within a planetary disk that sits at a 90-degree angle relative to the plane of the Milky Way galaxy. From the surface of that world, the brilliant, star-dense band of the galaxy would not cut horizontally across the sky. Instead, it would form a massive, vertical wheel of fire that spins directly overhead, passing through the poles of their planet. Their astronomers would look out along their horizontal planetary plane and see nothing but the empty, dark intergalactic void, while their vertical sky would be filled with the blinding glare of billions of stars. When that civilization developed their first primitive chemical rockets, they would inherit the same orbital velocity constraints that hold us captive tonight. Their rockets would easily glide along the flat plane of their local disk, traveling to their neighbor planets with modest fuel budgets. But to turn 90 degrees and climb out of their disk, to enter the path that leads toward the bright core of the galaxy, they would face the same insurmountable Delta V wall that bars humanity from looking down upon the sun. They would look out into the brilliant, star-filled vertical sky with an intense, agonizing sense of frustration. The most spectacular, star-dense regions of their universe would be located in the very direction that their physics makes hardest to reach. They would be stranded in a flat, dark planetary hallway, looking up through their vertical windows at a cosmic metropolis that they could see with absolute clarity, but could never visit without borrowing the immense, patient gravity of their own giant worlds. The geometry of creation is a universal architecture that builds the same hallways and the same prisons across every corner of the universe. The deep time of the invariable table. To sit quietly and contemplate the vertical axis of the solar system is to step out of the frantic, short-term rhythms of human life and enter the majestic, deep time of the cosmos. The flat tabletop of the invariable plane is not a permanent feature. It is a slowly evolving monument to the conservation of angular momentum. Over billions of years, the planetary disk does not remain perfectly rigid. It behaves like a giant, flexible sheet of metal, vibrating in slow motion. The gravitational tugs of the planets create long-period waves that ripple through the disk, causing the orbits of individual worlds to gently rise and fall above and below the true average plane of the system. Earth's orbit, which currently sits at a tiny tilt of 1.5 degrees relative to the invariable plane, has swung up to nearly 3 degrees and dropped down to nearly 0 over cycles that take millions of years to complete. During the periods of maximum tilt, our ancestors lived on a world that climbed significantly higher into the vertical sky every 6 months,